Alright, second model. Let's apply a distributed load on the right edge, but not according to the consistent node load. So this is not consistent node loading that we're applying here. It's still statically equivalent, because if I say 120 plus 120 plus 120 plus 120 plus 120, I still get 600, but it's not consistent node loads. Okay, and so far away the answer should be accurate, close by the answer should be inaccurate. So let's go and see what happens if you run this one. Then I've got magic. Alright, so this is the deformed and underformed structures. You can see there. There is essentially von Mises stress. And so von Mises, we are far away, we see we're still in that sort of ballpark. We are close by the place where we apply the loading. Things can go up quite largely. Okay. If you look essentially sigma xx, ballpark 150, far away, close by, large variation from 250 to about 50 on this edge here, sigma xx. Sigma yy, again far away, this edge here, we're in the 0 ballpark as expected. On this edge here though, quite a large variation of stress of minus 70 around this edge. Okay, so then some compressive stresses that we see here. You can nicely see this development of the stress field inaccurate, and getting more and more accurate as we get in. All of a sudden, far enough away from this, we start to get quite accurate. Okay. And then sigma xy, similar story. Far away is 0, close by it varies around 70, minus 70. Okay, so that's important to understand. Again, when I look at the reaction forces, I see beautifully minus 50, minus 200, minus 100, minus 200, minus 50. So that's the consistent loading that's popping out there. I see reaction force in the y direction 0, spot on as expected. Go through the same story. Equilibrium satisfies forces, sum of forces in the x direction, sum of force in the y direction, sum of moments, and again we could do sum of moments around a line, let's say around this point here. So what we know is essentially is that this distance is 1 millimeter, 2 millimeter, 1 millimeter, 2 millimeter distance towards this central neutral axis. And so you can say minus 50 times 2, plus 50 times 2, that's for the top and bottom, minus 200 plus 200 times 1, and then essentially minus 100 times 0. That's what we have. And then we can do the same for the applied loading, making sure we multiply by the distance they applied it, minus 120 times 2, plus 120 times 2, etc. All of that sum of moments tells us it's 0. Okay. The end calculation for stress, again 150 is expected, and here we're just summarizing again what is the stress far away. Okay, from where the load is applied is 150 is expected. Where it's close by, it can vary quite a lot. Okay, it can be quite different. Beautiful. Okay, so this is again just to remind you of what's going on. So model 3. Now we're going to model this with the consistent loading applied on the right edge. So again, 50, 201, and 250 load distribution. Don't forget, it's a unit thickness structure. And so essentially what we have is, we can run this and see what we get out. Now we look at, this is the response that we get. Now it's accurate, close by also to where we apply the load, because we're applying the loading now properly. So if we look at the Mises, 150 spot on, everywhere. Sigma xx, 150 everywhere. Spot on. Even closer we applied the load is now accurate. Can you see that? That's now accurate, 150. So that's essentially 0.0002 plus 150. That's it, plus 150, what that means. Very accurate. Next point, sigma yy, 0 everywhere. Very accurate. Even closer where we apply the load. Sigma xy, close. Very accurate everywhere. Even closer where we apply the load. So that's important to understand. If I look at the reactions, 0 at for the y1, minus 50, minus 200, minus 100, minus 200, and minus 50. And sum of reaction forces in x direction, minus 600. We know the total applied load is 600. So sum of force in x direction is 0, sum of force in y direction is 0, sum of moments around any line, let's call it y0, is also 0. So this is a stress is spot on everywhere. Okay, so the really big crux of Saint-Venant's principle that comes across here is, if we're interested in the answer close to where we apply loads, or where we, and so this is now, I'm talking in the context of applying loads, but because when we have prescribed displacement somewhere, they translate towards reaction forces. So the same arguments what I make here for load being applying loads also counts for applying boundary conditions. As long as they're statically equivalent, we can simplify prescribed boundary conditions. Again, with just understanding that if we look at the answer close to where we apply the boundary conditions, we'll be less accurate. If we simplify, we can have quite a variation in the answer there. But as long as we look sufficiently far away from that, where we made the simplification, whether it's now applied loading or whether it's applied boundary condition, doesn't matter. The reality is the answer will be accurate. Okay, as long as we look sufficiently far away. And so what the sufficiently far away means is it really is a function of geometry, etc., etc. But I mean, there's definitely some good guidelines on what can look at. But if you for instance have a structure where, let's say a rectangular structure like this, if you start looking away maybe one or two about, let's say, two heights, so these this height, if you look about two of these heights away from where you made the simplification, things should already start becoming quite a lot more accurate. Okay, so there's not a fixed answer what the answer is there, because there is if there's some variation there, it will take some distance that you have to be away for that effect to sort of dampen out. And the reason why we see this kind of behavior is just because we have a forgiving partial differential equation in the structural mechanics problem, which is essentially an elliptic partial differential equation. And in elliptic equations, things tend to die out or dampen out. So if you have some variation that you introduce here, that variation will dampen out as we move along spatially, which is different to some of the other hyperbolic kind of equations where things might actually propagate. Those variations that you might have made here might propagate. So please bear in mind, this is a structural mechanics phenomenon. It depends on the partial differential equation that you're looking at, whether Saint-Venant's principle counts or not. Okay, so that's just another important consideration. But hopefully this gives you a very good idea of the benefits and sort of the key insights of what Saint-Venant's principle is that as long as we look sufficiently far away from where we made a boundary condition simplification, things will be accurate, as accurate as if we've taken great care at modeling that very accurately. Okay, so reflection time. So different approaches to applying load to where the bars to bar the respective results were considered. Assuming the displacement boundary conditions were applied correctly. So what can be said about the deformation stresses on the right hand side face where the load is applied? What observations do you make with this regard to the deformation stresses on the left hand edge? Okay, so right hand edge can have large variations. That's where we apply the load, and only one of them gives us an accurate answer, and that is when we took great care applying consistent load loading. the observations we can make. On the right, the left-hand side is that all of the answers, independent of how we model it, was spot on. And so the question here is, what does it imply for the potentially large functions where the application of boundary conditions are uncertain? Okay, so sometimes we might not be 100% certain of boundary conditions, but we could maybe figure out what is a statically equivalent boundary condition. As long as we're not interested in the answer close to where we apply them far away, we can actually simplify quite a lot. So this is really important to understand. This Saint-Venant's principle allows you to decide where do you want to put your modeling energy, effort. Where do you want to put effort in? And this is an extremely important principle. It allows you to make modeling decisions of where should we take great care and where can we simplify loading and boundary conditions. Okay.